So, hello all of you, welcome to the session. Now, in this particular session, let us start with simple examples. Because last session we discussed classification of elements, right? Okay. Now, let us look at certain examples to identify. Once the waveform is given or once the characteristics are given, we must be in a position to identify which kind of element it could be. Okay, there is an element given. There is an element given here in this box. So what type of element it might be? It might be a linear element, it might be a nonlinear element. It might be active or passive. Okay, unilateral, bilateral, or combinations. It might be. Okay, the possibility, what is the possibility that we have? So the first question I would like to give you, what is this? Okay, you may have current or voltage, whatever, some current or voltage, or some current voltage, whatever it is. That's not a problem, okay? You can take current or voltage. So, how do you define it? Is it linear or non-linear? What is linear actually? Y is equal to mx. Okay, y is equal to mx. But for all even negative values of x, there should be y in proportion to this x, the y should also be present. Yes or no? But what's happening here? For all positive values of v, you have I, you have v, but for all negative values of I, there is no v at all. Yes or no, all of you? Okay. So what does it mean? Is it linear? It's not linear. It looks like straight line, but there is no characteristic in third quadrant. Okay. It should be extended, but it is not there. It's something like this. So what is this characteristics actually here? This characteristic is non-linear. Is it passive or active? Okay. It's definitely not passive, because passive element will have the characteristics in both first quadrant as well as third quadrant. Understand all of you? Okay. It is not passive. Okay. It does not mean that it's active. When it is not passive, it does not mean that it's active. Again, active element will always have the characteristics in both first quadrant and second quadrant. So 2 points need to be noted down. The first point is that, okay, passive element will have in first and third quadrant. Active elements will have in first and second quadrant. Understand? Therefore, it is non-linear. Yes or no? Non-linear. Unilateral. Why unilateral? You understand why it is unilateral. It is having flow of current only in one direction, no other direction current. Unilateral. Okay. That's it. It might be a non-linear element or it might be a unilateral element, no doubt. But it may not be active, because active element should have what? In both first and second quadrant. It is not a passive element, because it should be having what? First and third quadrant. That's what. So it is easy to identify now. Second example. What is this? Linear, voltage current or current voltage, doesn't matter. Anything is okay. Linear, passive, bilateral. Yes or no? Bilateral. Like that. Third one. What about this? Non-linear because saturation is there. Passive because it is having both in first and third quadrant. Bilateral Nonlinear because saturation is present. Passive because first and third quadrants. Bilateral because the property is same in both the, okay, with the reversal of current through it, still you have the same characteristics in first quadrant and third quadrant. Okay. Fourth one. Voltage current or current voltage doesn't matter. Anything is okay. What about these characteristics? Is it linear or non-linear? Definitely non-linear, because linear should have it should be extended in this quadrant, or else it should be extended in this quadrant. But what's happening here? There is no extension at all. So it is a non-linear. It looks like straight line. Don't get confused, I'm telling you. Non-linear. Definitely not passive. No doubt in that. Okay, definitely not passive. Yes or no? What is the passive element characteristics? First and third quadrant. So definitely not passive. But definitely active. There is a possibility for active. Unilateral, bilateral, no. I cannot say anything on that. These are definitely non-bilateral. I cannot say unilateral, but non-bilateral. Yes or no? Like that. You can say active. Active element may have in first and second quadrant. So non-linear, active, and non-bilateral. Yes or no, all of you okay? Here non-linear, passive, bilateral. Here linear, passive, bilateral. Yes or no, all of you okay? You can note down quickly. These are the very, very important examples. Okay, very, very good examples here. And important examples to understand. Now let us look at, before we enter into the network analysis part, okay, let us also discuss what is KCL and KVL. Okay, you already know what is the statement of KCL, what is the statement of KVL. So just let us quickly complete it. Okay, with certain examples also we will see. So what is Kirchhoff's current law? KCL and Kirchhoff's voltage law, KVL. First, let's start with KCL. According to KCL, write down please, write down all of you, the algebraic sum of currents, please write down, algebraic sum of currents entering into a node, algebraic sum of currents entering into a node is 0 at any instant of time. Algebraic sum of currents entering into a node is 0 at any instant of time. Okay, I think all of you understand that. Algebraic sum of the currents entering into node is 0 at any instant of time. Why we are mentioning at any instant of time? Okay, because sometimes the current might be 10 amperes, the current might be 2 e power minus 2t, the current might be here, okay, time varying, yes or no? Current might be constant or current might be time varying, 10 sine 4t plus 30 degrees. What does it mean? The sinusoidal current. So how do you really give a statement? How do you really give a statement, okay, when you have a current which is a function of time? Then obviously you must mention, because at every instant of time the algebraic sum of those currents must be 0. That is why we are mentioning clearly. So whenever somebody is asking the KCL, you must give a complete statement. What is that? Algebraic sum of the currents entering into node is 0 at any instant of time. Okay, this is I4. The degree of this particular node is 4. Degree is 4. Okay, so therefore n is equal to 4 here. Now when you write KCL, leaving current, the leaving current you can take it as positive, entering current you can take it as negative. Okay, nothing wrong in that. Even if you take reverse, it doesn't matter, because the equation is multiplied by -1, it does not make any difference. But I generally follow, okay, I generally follow this particular convention: plus I1 minus I2 plus I3 minus I4 is equal to 0. Okay, and you can write now I1 plus I3 is equal to I2 plus I4. Now summation currents, sum of leaving currents is equal to sum of entering currents at any instant of time, because as I said, or as I told you a little while ago, the current might be constant or the current might be time varying. So algebraic sum of the currents entering into a node is 0 at any instant of time. This is one statement. Or else we can give sum of the currents leaving, okay, from the node is equal to sum of the currents entering into a node at any instant of time. Okay, so please note down quickly. Note down quickly. We also see an example here. Let's note down this particular example, all of you. Let us find I1, I2, I3 in this particular figure. A simple example just to understand. I think all of you know very well what is KCL, but still let us try to complete it. As I told you that I am going step by step. Okay, keeping in mind all levels of students. So we generally discuss here, or I generally discuss here, step by step, so that every student will feel comfortable. Okay, and further after 10, 12 sessions, we accelerate it. Okay. Now look at this. To find I1, I can apply KCL either at this point or at this point. Any point is okay, but the problem here is I cannot apply KCL at this particular node because I do not know what is I2 and what is I3. But I know what is here the current 11 amperes and 14 amperes. If I apply KCL, leaving current plus I1, right? Or else sum of the leaving currents is equal to sum of the entering currents also can be written. So I1 is leaving plus 14 amperes is also leaving. But what is this 11 amperes doing? Entering. Therefore, I1 is equal to minus 3 amperes. Okay. Now coming to this. I2 is leaving plus 11 amperes is equal to 9 because this is entering current. So I2 is equal to minus 2 amperes. I3 is actually entering here. 14 amperes is entering, but 9 amperes is leaving. Minus 5 amperes. Hope you understand, all of you. It's very simple. Sum of the entering currents goes sum of the leaving currents. Quickly note down. Then we'll step into Kirchhoff's voltage law. Now let's go with the KVL. I think all of you are done with that. Now let's go with the KVL. KVL. According to Kirchhoff's voltage law, the algebraic sum of voltages in a closed loop is zero at any instant of time. Okay, once again, I think all of you understand why I'm using at any instant of time. Okay, let us take an example. Usually you apply KVL in a loop. Let me take some polarities randomly here. Okay, and this is a closed path. Let us say I'm taking here. It is part of one circuit. Let us say there is a big circuit. I'm taking a small part of it. Assume that the polarities and the voltages are available here. Now let us apply Kirchhoff's voltage law in this particular loop. Okay. So KCL we apply at a node, but KVL we apply in a loop. Now, but KVL generally we apply either in clockwise direction or anti-clockwise direction. Doesn't matter, right? So let me go in the clockwise direction now. If I go with the clockwise direction, look at this. Okay, look at this. When you are taking the loop here, A, B, C, D, A, this is a loop, right? Clockwise direction you are taking. You are moving from plus to minus here, minus to plus, plus to minus, minus to plus. That means you are coming across two kind of polarities. One is plus to minus. Two situations you are coming across. One is plus to minus, the other is what? Minus to plus. When you are moving in the clockwise direction, you come across plus to minus is one category and minus to plus is another category. Two categories you are coming across here. So what is plus to minus actually? When you are moving from higher potential to lower potential, usually there is a decrease in voltage, or else you can call it a fall in voltage. Fall in voltage. Okay? You can call it fall in voltage. And when you move from negative to positive, you call it increase in voltage or rise in voltage. Rise in voltage. Just like leaving current and entering current, what you have assumed, the leaving current is positive, entering current is negative. Similarly, you can also take the same way. The fall in voltage can be taken as negative here, and rise in voltage can be taken as positive. Some people take rise in voltage negative, fall in voltage positive. Don't worry about that. Even if you multiply this equation by -1, it does not make any difference. For that reason, you can take anything that you want. But I generally follow this way. The fall in is negative, rise in is positive. Okay. Now, what is my loop that I have selected here? A, B, C, D, A clockwise. You see plus to minus. That means minus V1. Minus to plus, plus V2. Plus to minus, minus V3. Fall in voltage. This is rise in voltage. Plus V4 is equal to 0. I can write it as V1 plus V3 is equal to V2 plus V4. And again I can write it as V1 and V3. What is V1, V3? Tell me all of you. V1 is a fallen, V3 is also fallen, right? So sum of fallen voltages is equal to V2, V4 what? Actually here rise in voltages, right? So rise in voltages. Sum of fallen voltages is equal to sum of rise in voltages. So this is how you can write. Okay. So please complete it quickly. All of you know KVL, KCL very clearly. I know that very well, but still let me complete it. So that any doubts are there, we need to really, you can get rid of all the doubts once we start with the fundamentals. Okay. Note on this. Meanwhile, I just give you a problem here. One example. Okay, so please note down this particular problem as well. Let's try to find V1, V2, V3. V1, V2, V3 values. Note down quickly. So now you can see V1. To find V1, I can apply KVL in this loop or in this loop or even in this loop. Remember, in every loop KVL must be satisfied. Yes or no, all of you? In every loop KVL must be satisfied. These are the fundamental loops, and you have even other loops also. It's not that only fundamental loops KVL must be satisfied, in other loops not required. Not like that. In every loop KVL must be satisfied. And at every node KCL must be satisfied. Say you have 100 nodes, 99 nodes are satisfying Kirchhoff's current law, but one node is not satisfying. What does it mean then? The circuit is invalid. The circuit is no longer valid because at one node the KCL is not satisfied. So what is this that 99 nodes are satisfying Kirchhoff's current law? Yes, that one node is missing and the one node is not satisfying KCL. Therefore the circuit is invalid. If you have 100 nodes must satisfy the Kirchhoff's current law. Similarly KVL, if you have 100 loops, I'm not saying fundamental loops, 100 loops, then KVL must be satisfied in every loop. Understand all of you? Okay. Well, now coming to this. KVL can be applied here, clockwise or anti-clockwise. Let me say clockwise. So what is this plus V1? Okay. And minus 10 minus 2 plus of minus 5 is equal to 0. This is how you apply the KVL, right? Plus V1 minus 10 minus 2 plus, that means rising. This is a fall in voltage. When you move in this direction, this is the rise in voltage, fall in voltage and rise in voltage. That's it. But I can also write something like this. Directly V1 is equal to, when you have potential difference between 2 points anywhere in the circuit, you can apply this concept called touching concept. Okay, how you apply that? You start at plus and reach minus, selecting any path. Plus to minus, you can go like this, you can go like this, you can go like this. Yes or no? There are many ways to reach the plus to minus. Start at plus and reach minus. Okay, directly you write V1 is equal to, okay, directly you write V1 is equal to, and start at plus. I am choosing this path. You're touching positive sign first, therefore plus 10. You're touching negative sign first, therefore minus. But already what is the value? Minus 5. Okay. Therefore, you got 15 volts. We applied KVL only, but just to speed up the calculation, nothing else. Okay. How do you find voltage between 2 points anywhere in the circuit? KVL, absolutely no doubt. Okay. But you can also name it as a touching concept to speed up the calculation. V1 is equal to 10. Look at this. V1 is equal to, you're touching positive first, then negative first. That's it. Can we apply the same thing for V2? Look at this V2. KVL, but I'm applying the touching concept. Plus to minus. Plus to minus, choose a path. This is a plus, this is minus, right? This is plus, this is minus. I can reach plus to minus like this, but I do not know values. I can do like this also. This is also a path. Yes or no? This is also a loop. Yes or no? KVL must be satisfied in that loop also. But you do not know the value of V3. But if you choose this, tell me, V2 is equal to touching positive plus 10. Touching plus, but already what is the value? Minus 20. Touching negative, but already negative value. Again touching plus, but it is already negative value. Minus 60. Let me write it clearly. 10 minus 20 plus 30 minus 60. You tell me now, what is this value? This is 80, this is 40. 40 minus 80, this is minus 40 volts. Hope you understand this. Similarly, V3. What is V3? Look at this, all of you. What is V3? Let me start at plus and reach minus. Starting plus, right? This is the path I can choose without knowing V1, V2. Without knowing V1, V2, can I find V3 or not? Yes, I can find. Look at this. I can choose this particular path. Okay. So V3 is equal to plus of minus 5. Okay. Plus of minus 20. Touching positive sign first. Then minus of minus 30. Then plus of minus 60. So what is this? Now minus 5, minus 20, plus 30, minus 60. Now you tell me here, what is the value? This is minus 25 and this is 60. So minus 85, 30 minus 85. So what do you get here? Minus 55. Note down this, please. Note down all of you. But a quick brush up of all these concepts, okay? I think you have done with that, okay? Now let us look at another important topic here. Network reduction. But before that, better you write a point here. Note. First point. In a given network, KCL must be satisfied KCL must be satisfied at every node. At every node. At every node. Otherwise, the network is said to be invalid. Second point. In a given network, KVL must be satisfied. Please write down. KVL must be satisfied in every loop. Otherwise, the network is said to be invalid. The network is said to be invalid. Understand? So very clear, all of you? I think you have written this too quickly. Now let's put the heading network reduction. Network reduction. I think all of you written that. Put the heading network reduction. So we divided the network theory into two parts. One is the network analysis and the other is network synthesis. Now we started our journey with what? Network analysis. Yes sir? We started our journey with the network analysis. What do you mean by network analysis? For a given input, for a given network, you are supposed to find the output. Current output or voltage output or power output. Yes sir? But to find all this, one must really understand how to reduce a network. You might be having series combination or parallel combination. You have only two combinations basically available. Yes or no? What are the basic two combinations you can connect? Tell me. Either in series or in parallel. Yes or no? Okay. So let us look at first by taking the resistive elements. Okay. Let us see how we reduce a network. First, we apply this reduction for what? Resistors. And then we see for inductors, capacitors, anyway we are going to see that, and we can generalize for inductors and capacitors by simplifying the resistive elements. We can generalize even how the reduction takes place and how the formulas can be appearing, or how the formulas look like in the case of inductors and capacitors. Easily we can do that. Okay. And anyway, that reduction we are going to discuss inductors and capacitors separately in the separate topic in the third particular chapter. I told you that inductors and capacitors I'm going to discuss. So in this particular topic, first we start with the resistors. Then we apply the same reductions not only for resistors but also voltage sources, current sources. Okay, how we can reduce, that we'll see. First, let me start. All of you put the heading, network reduction. Put the heading, network reduction. The first basic combination is of what? Series combination of resistors. Series combination of resistors. Okay, two elements are said to be in series. When do you say elements are in series? When do you say? Tell me, all of you. When do you say the elements are in series? Yes. The elements are in series if the current flowing through these elements is same. If current through R1 and R2 is same, then we can say they are in series. And of course, if you apply the voltage across them, the voltage will certainly get divided. Okay. So why current same? Why voltage gets divided? That's another point here. Okay. When you connect the elements in series, okay, why the current is maintained same? Why the voltage is getting divided? Okay. Series combination of resistors is nothing but what? Current is same and voltage gets divided. Why current same? Why voltage gets divided? What is the reason? I mean, on what basis you can say current is same and voltage gets divided? Remember, any question that you come across in network analysis, you can answer those questions using the two important laws, KCL and KVL only. Your answer is always with respect to the KCL or KVL. That's it. Look at this. The current is same in order to satisfy Kirchhoff's current law at every node. Just now we have seen the statement that every node KCL must be satisfied. Otherwise you call that circuit as what? Invalid circuit. Similarly, at every loop or in every loop KVL must be satisfied. Otherwise you call it as what? Invalid circuit or invalid network. Look at this. Look at this. This is a node. This is a node. What is the current actually entering here? I. What is the current leaving here? I. Therefore, the KCL is satisfied or not? Sum of entering current is equal to sum of leaving current. This is also a node. I think all of you remember the definition of node. Degree must be 2. Yes, the degree is 2. I can call it as a node, no doubt in that. What is the current entering here? I. What is the current leaving here? This is also I. That's it. That's why current must be same in both the elements to satisfy Kirchhoff's current law. Similarly, current is entering I, current is leaving is how much? I. Entering I, leaving I, KCL is satisfied. At every node, KCL is satisfied here. How many nodes are there? 1, 2, 3, you can say as per the definition of a node. Therefore, why current same? In order to satisfy KCL. Why voltage divides? If voltage is not divided, the KVL won't be satisfied. Yes or no? The algebraic sum of the voltage must be 0. Or sum of these two voltages must be equal to total voltage. So in order to satisfy KVL, the voltage gets divided. I think you understand now. Any question that I ask you, why current same, why voltage divides, why current should be like that, why voltage should be like this. For all those questions, you can answer with respect to either KCL or KVL. When I talk about current, KCL. When I talk about voltage, KVL. That's it. Okay. So it's very clear now. Well, now if you take RAB, when n number of elements are connected in series, okay, I is equal to 1 to n summation Ri. And no doubt, the effective resistance will be always greater than even the highest value of R1, R2 and so on what? Rn. If you take GAB, that means conductance. Conductance is the reciprocal of resistance, 1 by GAB. Then summation I is equal to 1 to n 1 by GI. But I want GAB. Therefore, I can write that GAB is equal to 1 by summation I is equal to 1 to n 1 by GI. Remember, GAB, effective conductance, the total conductance is less than even the lowest value of G1, G2 and so on Gn. Understand? Usually we remember the formulas for n is equal to 2. RAB is equal to R1 plus R2. GAB is equal to G1 G2 by G1 plus G2. You can just substitute here and simplify. Finally you get that value. But remember, when you have more than 2 elements, better you deal with this particular formula. Okay? Please do not generalize it unnecessarily. Don't get confused. Better you go with the formula, general formula here. Okay? You can just go with the general formula when n is more than 2. Okay? Now let us apply Ohm's law to the individual elements. V1 is equal to I into R1. V2 is equal to I into R2. From this, I understand V is directly proportional to R or inversely proportional to G. Real? Therefore, V is equal to, you also know that V1 plus V2. V is equal to V1 plus V2. From this, we understand V1 is equal, because V is directly proportional to R and V is getting divided. How the V is dividing here? In proportional to the resistance. Therefore, V1 is equal to R1 by R1 plus R2 into V. V2 is equal to R2 by R1 plus R2 into V. Okay. This is called, you call it voltage division rule. But the same voltage division rule we can express in terms of even conductance. Because you can see R1 can be replaced by 1 by G1, 1 by G1, 1 by G2. Yes or no? Therefore, I can write it as, finally after simplifying that whole, G2 by G1 plus G2 into V. And V2 is equal to G1 by G1 plus G2 into V. The voltage division rule in terms of resistance, voltage division rule in terms of conductance, you can remember both of them. And the voltage across kth element, let us now generalize for kth element voltage when n number of elements are connected in series. Okay? V1, R1, Vk, Rk. Therefore, Rk by summation I is equal to 1 to n Ri into V. But you also know that resistance is nothing but what? Reciprocal of conductance. Okay? Yes or no? Therefore, 1 by Gk, you can even express the same in terms of conductance. I is equal to 1 to n 1 by Gi into V. This is the expression for what? Voltage across kth element when n number of elements are connected in series. Okay? So when more than 2 elements are available, you can really deal with this formula, and it's very clear. Okay? Inductance formulas look like resistor formulas and capacitor formulas look like conductance formulas. You can remember always like this. Okay? Please have a note of all this quickly. Then we deal with the parallel combination. Once this is over, we can deal with the parallel combination. Okay, so you can write this one is what? Voltage across kth element. When n number of elements are connected in series. Okay. So students, we stop this session here. Okay. And the next session we start with the parallel combination of resistors, and then we see some important problems in that. How to reduce the network when some problems are given. There are some around 20 problems are given. We will discuss them. Okay. I'll stop here.